Hello everyone. So we're in Unit 6, Part 2 still, factoring, and right now we're going to look at factoring special cases. This corresponds with assignment 9, and so when I say special cases, we're talking about a difference of two squares and perfect square trinomials. So you've already learned how to multiply those together and what happens when you do that. Now we're going to learn how to factor them back apart. So with your difference of two perfect squares, one thing that you're looking at is to say, well, the first term, so x squared, we want to know, is that a perfect square? The last term, is that a perfect square? And is there a difference between them or a subtraction in the middle? So those are three things you need to look for. We want both terms perfect squares. And 2, is it subtraction? And if you can say yes to both of those, then it's a difference of two perfect squares. Now, don't forget you can also rearrange your terms to make it subtraction if you need to, so keep that in mind. So what we're really factoring here is something where the b term is 0. So thinking back to our trinomial, find two numbers that multiply to negative 25 and add to 0. Well, 1 and 25 doesn't work, but 5 and 5 would work if we need a negative 25. So this would factor into x plus 5 and x minus 5. And that will be true every single time. So because you have these opposite signs here, when you FOIL this back together, you'll get x squared minus 5x plus 5x, so those are canceling, and then a minus 25 at the end. So you're always going to have these types of factors where the first part in the binomial is the square root of the first term. The last number is the square root of the last term, and then you have same values in your parentheses, just opposite signs. Alright, so to generalize, okay, so looking back here, x squared plus 25, now this over here, you have your two perfect squares, but it's not a difference, okay? So this polynomial is actually prime, it's not factorable, alright? If we put a negative in front, then we could rewrite it as 25 minus x squared, and now it's factorable, it's just backwards, 5 minus x and 5 plus x. Alright, a squared minus b squared factors into a plus b and a minus b, no matter what you have there. Okay, so that's your difference of two squares in a simplistic version. Now let's look at one where we have a little bit more going on. So I see, first of all, the first term, 9x squared. Well, 9 is a perfect square, and x squared is a perfect square. 36 is a perfect square, and there's a subtraction in between. So I want to think about this as, well, 9x squared is really 3x all squared, and 36 is really just 6 squared. So when I'm factoring this, these two parts, 3x and the 6, are what are going to go into my factors. So we end up with 3x minus 6 and 3x plus 6. And remember, you still can always take out a greatest common factor if that's possible. So in this case, I know 9 times 4 is 36. So I could have started by taking out a 9 and saying, well, then we have left x squared minus 4. Well, this is still a difference of two squares because x squared is a perfect square, as is 4. So your full factor would be 9 times x minus 2, x plus 2, because 2 is the square root of 4, and x is the square root of x squared. And you can see that from the one we did above, because both of these have a common factor of 3. So you can pull a 3 out of the first factor, and a 3 out of the second factor. And, well, 3 times 3 is really 9 because all of the stuff is multiplied together. So you get the same completely factored version as we did below, using the same method, really. You're just, one of them you took out a greatest common factor first, and one you did it last. So when we look for something completely factored, this is what we're looking for. This version is considered factored, and you can still find your important information like zeros from this. It's just not completely factored because there's a greatest common factor. All right, and the second type of special cases is a perfect square trinomial. So the difference being here, we're still working with perfect squares, but we're not looking for subtraction anymore. We're looking for two numbers that are the same, that multiply to the end and add to the middle. So in this case, the two numbers that multiply to 9 and add to 6 are 3 and 3. So your factors are x plus 3 times x plus 3. Well, since we have two of them that are exactly the same, this is really x plus 3 quantity squared. Right? And so that is what we're working from. So anytime you have something, and we looked at this before when we were multiplying, like a plus b squared, if you multiply that out and FOIL it all out, it's a squared is your first term, b squared is your last term, and 2ab, or 2 times a times b, is your middle term. And so if you're given something in this form, you can factor it into the a plus b squared. So let's look at one that's a little bit more complex. 64x squared plus 48x plus 9. So just like we did with the difference of two squares, I'm going to try and write it in a form where you can see what's being squared. Well, 64x squared is the same as taking 8x and squaring it. 9 is the same as taking 3 and squaring it. And so what we have to check for here to see if it's a perfect square trinomial, or a PST, is if the middle is going to be 2, and then 8x becomes our a, and 3 becomes our b. 2 times a, which is 8x, times b, which is 3. And so this, just a heads up here, a and b are now referencing different things than when we were graphing quadratics. They're just referring to two parts of this polynomial. But let's check out the middle. So 2 times 8x times 3, well, 2 times 8 is going to give me 16. 16 times 3 is going to give me 48x. So yes, it's in this form. It's a perfect square trinomial, which means we can factor it into a plus b squared. So we get 8x plus 3 quantity squared. So what these tricks really are just shortcuts, essentially. You could take this same polynomial squared plus 48x plus 9, and we could factor this by using slide and divide if you didn't recognize it was a perfect square trinomial. So sliding 64 to the end, and we need 9 times 64, or 576. And then we're in charge of factoring that, so figuring out what multiplies to 576 and adds to 48x. And well, I know, because I know it's a perfect square trinomial, I also know that 24 and 24 are going to multiply to 576. And I also know that they add to 48, so this is x plus 24, x plus 24. And then because we slid the 64 to the end, we then have to divide that back out. So you're dividing this by 64, as well as this. And this is going to be able to reduce. So you get x plus 3/8. And over here, x plus 3/8. And then if we're left with a fraction, we pull that number back in front. So you get 8x plus 3 quantity squared, because you have that twice. Same thing that we got from the perfect square trinomial, but we just did it a different method. So it's not a big deal if you don't recognize it's a perfect square trinomial off the bat. But if you do, it can make this process a lot faster for you than trying to figure out, factors of 576. So go ahead and take some time and work on assignment 9 and see how it goes. And come see me if you need help.